All right, we're doing this one cold. Normally, everyone we go through these lessons beforehand, but this one we're just jumping in. We're gonna get like an authentic experience here. Let's do it.
Woo.
Um,
Nice shirt, Mr. Kirk.
nice shirt. Most likely, if you're watching this on Sunday, which I suspect most people would do for a Monday class, right? Watch it on Sunday. You're definitely not watching it Monday morning at 8 a.m. There's no way that's happening. If you're watching it on like Thursday or Friday, go you. But you might be watching this on Sunday, and Sunday is Pi Day.
Uh-huh.
I like how we have the same Pi Day shirt. Like
But
we've
it's
had
but it's like live every day like it's Pi Day. So
live
then it's not even like we need to say like, oh, like Sunday or whatever. It's like it's Pi Day.
right, even
This
if
is
it is Monday
because
at 8 a.m.
it's because we chose this shirt last year because Pi Day was not on a school day. So then we it was like funny.
I like this a lot. And then Pi Day this year we're celebrating on a Friday, but
Mm-hmm.
but it is on a Sunday, so same thing.
Yep.
I particularly like this Pi Day shirt. It feels really good.
Nice. $6 tees.
Is that the
But
name
they're
of the?
actually not.
Is that how
That's the
much they
website.
are? That's the website. What?
Yeah.
This is $6 t-shirt.
I think we had to pay for shipping also, so it was like $8.
Okay. Well, you know what? $8 for a soft quality shirt that
Yep.
has pie on it. I'm a
Mhm.
fan. How far out did we go? It does not imply that it keeps going. I got a problem. This is a rational number. Anyways, let's go ahead and get started. Let's title our page.
Are you sharing your screen?
I'm not, but that's what you're here for, to call me out when I do silly things like that.
I noticed you also strategically didn't share the Kami doc, so then I can't grab you. It's very
Oh, let me
clever,
do it.
Mr.
Let me do it. It's so easy. Boom, boom. Throw it in the chat. You know, I got a comment recently in one of the journals saying watching the video taught them how to, I forget what it was, but it had something to do with Kami. So I'm really glad that that's the case, that we are doing a Kami demonstration while also learning math.
Yeah.
If that makes any sense. All right, today is Pi Day, or we're pretending it's Pi Day. Wow, my drawing pad has been a little bit lame lately. Hopefully it's not. I think I need to change out the tip of the pen. And then it's, how about let's do this? It's a 22 over 7th period. That's
that's cringy.
You don't like that? You don't like 22 over 7 being an approximation for pi?
No.
No? Anyways, let's go ahead and get started. Today is an
Read it.
important lesson. I am sharing the screen now. Cool.
Yep.
We're going to derive something called the sum and difference identities. Right? Identities meaning we're going to get an equation that is always true. It's essentially a formula. And they're very useful. And we're going to derive one geometrically, cosine alpha minus beta, the difference formula, the cosine difference formula. And then we'll use that to derive the cosine sum formula, the sine difference in sum formula, and the tangent difference in sum formula. Oh, you already crapped. I like that crap. Already crapped. And then we'll use them twice. We'll calculate the exact value of pi over 12. Currently, we cannot do that. It is not one of our reference angles, pi over 6, pi over 4, pi over 3, and their multiples, pi over 12, and 5 pi over 12, tangent of 5 pi over 12. So we are going to derive a formula using our knowledge of geometry, and then apply it algebraically to some other things. Let's go ahead and get started.
Cool.
Right, so I did say we're going into this thing cold. I got an obnoxious picture here. There's a lot going on.
Oh no.
The first thing I want to do is I want to add something to this. And I think this is going to make sparks fly in your brain.
Mm-hmm.
I'm going to call that length 1.
Okay. So now we have a unit circle. And that's really helpful because we know we can like describe all of those coordinates as sines and cosines of our various angles.
So we have these three coordinates here. Okay. And just so the students are thinking as well, we want to create a formula for cosine alpha minus beta that is in terms of functions of alpha and functions of beta. So currently we have a function with the input being alpha minus beta, some angle. We would like a formula that we can take that number like pi over 12 and then break it up into the, I think this is right, pi over 4 minus pi over 6. 3 pi over 12 minus 2 pi over 12 is pi over 12. And if we can write cosine alpha minus beta in terms of functions of alpha and beta, alpha being pi over 4, beta being pi over 6, we can then evaluate cosine of pi over 12. So we need a formula with in terms of cosine alpha, cosine beta, or sine alpha and sine beta. That was a mouthful. You mentioned coordinates earlier. For example, let's call this A. What is A's coordinate?
A is that has to do with beta. It's linked with beta. And then for the x value, that's going to be cosine. And then the y value is sine of beta.
Yeah. So we're given the angles. And once given the angles, we can find the coordinate by plugging it into cosine and sine. What is this coordinate down here in the third quadrant?
So are we saying that alpha is that whole arc? Or that whole angle? Okay. So then we have, can we call that a different point like B, or should we just refer to it? Okay. So then that's cosine of alpha comma sine of alpha.
Sweet. And how about this third coordinate up here?
So I guess for the sake of continuity, let's label that C. And that would be cosine of alpha minus beta, which is the formula that we're looking for, comma, sine of alpha minus beta.
Awesome. So we need to relate these coordinates somehow. We need to relate these coordinates somehow. We have a bunch of segments, and we need to get some sort of equality. So I'm gonna go ahead and change the color. Actually, we've been doing this in I was gonna call blueberry because we're dealing with pie today. Let's go to blue, which doesn't actually is not actually the color of any fruit.
But is the color of Cookie Monster, who loves pie, probably?
I think Cookie Monster likes pie. Okay, we need to relate these coordinates. Think geometry.
Okay.
And this picture. Are there any, what is something that we can actually quantify in the coordinate system?
Well, distance is something that we typically like.
Mm-hmm.
So maybe we could use some distances, because that makes us have triangles, which we also like.
Okay. I like where you're going. Distances is the move. What distances in our coordinate system that we have here are congruent?
Congruent distances. Well, because we're taking alpha minus beta, right? So then from C to point B, do we have anything in common with like point A to something else?
Is the distance from B to C the same as the distance from the origin to A?
The origin?
They kind of look like it, right?
Of our wrapping function.
I don't mean origin. Sorry. Yeah.
Okay.
What is that coordinate? Just so we can have it written down.
That's 1, 0.
Yeah. Let me go ahead and add that. I said origin. I'm super sorry, everyone. I totally meant just the coordinate 1, 0.
But that makes sense that you called it an origin. Like I understood because I was thinking wrapping function.
Mm-hmm.
That's where you start.
So yeah, when we measure angles, we start at that coordinate 1, 0.
Mm-hmm.
Are those two distances the same? I don't think so. I mean, they might look the same. They might, like in this picture, be the same. But I think it just depends on what alpha and what beta are.
Okay.
If beta is a tiny angle and A is a large angle, they might not actually be the same length, but they might. What's the distance? What's the angle between C and B? Actually, I think that might be beta, right?
Is it beta? Because in order to get from alpha to there, or from alpha minus beta to there, you get out of beta.
Yeah, so I think that is beta. I think these lengths are the same, guaranteed. That's nice.
That is nice. I know that's where you're going, though.
I'm actually curious to see if that works. I don't think we should do it in this video, but that might be a congruence that will lead to at least a formula. Those are the same. We could find this distance, and set them equal. Do you mind if we do what I had planned in my brain just so we're guaranteed success?
Absolutely. Maybe this could be something that a student journals about.
Yeah, because what I'm going to do, and from here, I'm just going to kind of say what I anticipated you to say, and that is this distance and this distance are the same. But this might very well be the same formula as the other one. I just don't want to go down that rabbit hole in the video.
That's fair.
That would be totally something worth doing in class, seeing if that works. But those two lengths are exactly the same. How do I know they're the same? This angle is alpha minus beta. This angle is alpha minus beta.
Oh, I like that.
And then they have the same legs, 1, 1, 1, and 1. We got side angle side here. These two triangles are the same. So the blue segments that I've drawn here are the same length. I know for a fact that this will help us derive the formula, so we're going to go with this one.
All right, cool.
Really curious, though, about the other one. All right, so what is the length between B and A?
Well, we can use the distance formula. So we have... I'm
going to call that D, by the way.
Okay. So between A and B, we have the square root of the difference of cosine of beta minus cosine of alpha quantity squared.
Cosine beta minus cosine alpha quantity squared.
Plus sine beta minus sine alpha quantity squared.
That is correct. Yep.
That'll give us our distance. Okay.
That's just x2 minus x1 and y2 minus y1. You went from A to B. Nice. Awesome. Doesn't matter.
Oh, okay. Cool.
And then what is
CD.
the length from C to D?
We have square root again of cosine of alpha minus beta minus 1 quantity squared.
Cosine alpha minus beta minus 1 quantity squared. Hopefully I don't run out of room.
And then plus, well, this one doesn't have anything else, right? It's just sine squared of alpha minus beta.
I like how you said it. I'm going to put the square on the outside just so that we look the same across, but we'll bring that square to the right of the n in a second. Cool. Okay. We have this is the formula. It relates cosine alpha minus beta with a bunch of functions of just alpha and beta separately. Inconveniently, though, we don't know this. So hopefully we can do something. When given something disgusting like this, what does your brain say to do?
I want to square both sides.
Let's square both sides. Let's simplify. So if you square both sides, we're going to get cosine beta minus cosine alpha quantity squared plus sine beta. Sorry that I really need to go and find a new tip for the pen.
I thought they came with like a little pack.
They do. I just need to like find the pack. All right, so this is a little bit tedious, but I promise you the rest of the lesson won't be as tedious. Once we've done this first formula, and I'm actually going to do it now, bring that to here. I think things are going to be kind of nice in a second.
That's encouraging. Let's see, should we like multiply out?
Let's multiply out.
Okay.
So we got, and I think you're going to see something in a second. I'm very excited. Because
Okay.
I always get giddy when I see it. Minus 2 cosine beta cosine alpha plus cosine squared alpha plus. You just noticed it. I can hear that you noticed it. And hopefully some of the students are noticing it. But if you haven't yet, that's fine. You'll see it in a second. Sine beta sine alpha plus sine squared alpha.
There's another one.
Cosine alpha minus beta squared minus 2 cosine alpha minus beta plus sine. Oh, I forgot something. I forgot a plus 1. That minus 1's being squared plus sine squared alpha minus beta. Really tiny.
Cool.
You got the link. Do you want to circle some stuff?
I do want to circle some stuff. How did you know? We have cosine squared, sine squared, and we've got cosine squared and sine squared. And we got...
It's a Pi Day miracle.
This is pretty cool.
This is, no one's ever this excited about algebra.
Why?
Maybe Mr. Schwartz. He loves algebraic things like this. But I don't know. I'm doing algebra. I'm like, oh, this is kind of tedious. But when this happens, this is like
This is Pythagorean identities,
kiss.
right?
I know. I love when the Pythagorean. Those are all ones. So they don't disappear, but they become something.
Two.
They become the multiplicative identity. Cool. 2 of the multiplicative identities. And then are you writing the next line right now or no?
I'm not.
I'll start writing the next line.
I'm just excited.
So the cosine squared and the sine squared are going to become a 1. And the cosine alpha and the sine alpha are going to become a 1. So we're just going to get 2 from them.
Wait, there's also on the other side.
Yeah.
What?
It's like unreasonably satisfying.
Wow.
And then that combined with this one
is 2.
Also becomes a 2.
And they're the same.
Do you see how many 2s we have going on here?
Wow, too many 2s.
Too many 2s. All right. What is your heart desire here?
We want to take away some 2s, yo.
Chop, chop.
All right. And then can we just like divide by 2 everywhere?
Let's divide by negative 2 everywhere.
Negative 2.
I want cosine beta, cosine alpha, plus sine beta. That's a sim, not a sine. This is not Sims 5. Cosine. There's the formula. Whoa. I do want to reorganize it for a very specific reason that you'll see in a second. But we have now related cosine of alpha minus beta with things in terms of alpha and beta separately. So going back to that original problem, if asked what is the cosine of pi over 12, instead you can rewrite it as cosine of pi over 4 minus pi over 6, and then break it up into a bunch of things that we can evaluate.
Hey.
Right. The real purpose of this formula is not to evaluate cosine of pi over 12. It is a great exercise to remind yourself of the formula, but these formulas are going to lead to a lot of really cool tricks and manipulations in calculus. Mind manipulation. So keep that in mind. We're going to train ourselves with these formulas with some pretty good convoluted problems like evaluate cosine pi over 12, but there's a larger goal out there to know these formulas and be able to use them. So I'm going to rewrite this thing. Cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. And I'll explain a little bit later why I've reorganized it, but it should be kind of clear. Now we're alpha betical. We're alphabetical now, which is nice. It's a
So cosine, cosine, sine, sine. Did I steal your thunder?
You didn't steal my thunder, but we're gonna come back to that in a second.
Okay.
Cosine. So we can kind of address it right now. So we got cosine of alpha minus beta. The answer to expand this into the formula with alpha and beta separately is cosine the first angle, cosine the second angle, cosine cosine. And then we have a minus sign here. We're going to change the sign. And we're going to spell sine with a G. Cosine, cosine, sine, 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 sine alpha, sine beta. So there is a trick to remembering this, but we'll come back to that.
Okay.
Let's get the cosine alpha plus beta formula. And I mentioned we're not going to do another geometric proof. We want a formula for cosine alpha plus beta.
Well, adding is the same as subtracting a negative.
And then in a second, we're going to use your mnemonic device, cosine alpha minus negative beta. What's your mnemonic device?
Cosine, cosine, sine, sine, sine.
Cosine the first angle, cosine the second angle.
Cosine of negative beta.
Plus. You're having a field day right now. I love it. Sine, sine with a G. You can hear it when I sine. That's the sound of a G. Minus becomes a plus. Sine of first angle, sine second angle.
And sine of a negative is the negative.
So,
it's odd.
What'd you say about the cosine negative beta?
Well, because cosine's even, so when you put in the opposite, you still get out the same.
Yeah, so it just gets absorbed. And then what about this plus and this minus over here?
Well, they're going to swap.
We're going to swap. That negative's going to pop out, make that positive negative. Sine. Does your mnemonic device still work?
Cosine, cosine, sine, sine, sine. The sign changes.
Cosine, cosine, sine, sine, sine. It doesn't matter.
I don't like how we say sine, though.
You don't have to do it that way. I'm going to do it that way.
All right.
Cosine, cosine, sine, sine. It is the best way I've ever heard any formula in math being memorized. Like you got back in like geometry, the quadratic formula song. That's all nice, but it just doesn't feel like it just feels. I don't enjoy it. It's the best. Sine, sine, sine. Cosine, cosine, sine, sine, sine.
I wonder if there's something for sine, like a sum or a difference.
Let's find out. All right, so let's derive the formula for sine alpha minus beta, sine alpha plus beta, in terms of functions of alpha and beta. And maybe there'll be a mnemonic way to remember the sine formulas. Hopefully that cosine one's already drilled into your brain. Cosine, cosine, sine, sine, sine.
Sine, sine.
Oh, the beatboxing doesn't work. Okay, let's try to get one for sine.
Okay.
Sine. Do you want to do alpha minus beta or alpha plus beta first?
Let's do minus since it's written first.
I like that idea. All right, so sine alpha minus beta. Thoughts?
Co-function?
Oh, all right, let's do that. So we have the formula for cosine. Let's turn this into a cosine and then use that formula.
So half a pi minus the thing.
No one's ever said half a pi to me before, but I like that. Anyways.
At the grocery store nearby where I live, they've been selling half pies, but it's actually one pie.
But it's like the size.
Because it's a pie that they cut in half. But then, so they're selling you.
Get out of here. Should we start calling a full pi a tau? Anyways, tau is the 2 pi constant. Okay, let's do this. Cosine pi over 2 minus quantity alpha minus beta.
Cosine, cosine, sine, sine, sine.
So let's do that, and tell me what happens. So cosine the first angle, pi over 2. Cosine the second angle, alpha minus beta. Change the sign. Sine first angle. Sine second angle. What's going to happen? What's cosine of pi over 2?
Well, that's 0.
0. So this is going to go away. And then sine of pi over 2 is 1. So you told me,
like showed an identity.
You showed me that sine of alpha minus beta is equal to sine of alpha minus beta.
Ooh.
Nice. That's like telling me that 1 is equal to 1. I get it.
What if we distribute that negative a little bit?
I like that idea. Let's see what happens. Cosine pi over 2 minus alpha plus beta.
Oh yeah, we could do it with that, right?
Because this is good. This is kind of taking that pi over 2 out of isolation. We're grouping it with the alpha. So cosine first angle. Cosine pi over 2 minus alpha. Cosine, sine. I have a plus, it needs to become a minus.
Okay.
Sine. Okay.
Okay. So now we have cofunction, right, for sine. So we could flip that into cosine. And then we also have cofunction for cosine. So then that's cosine instead of sine of pi halves minus
Boom.
alpha. Cool.
There it is. Sine, cosine, cosine, sine. Sine,
cosine, sine.
Notice we didn't say sine.
Because there's no sign change in the middle.
There's no sign change. Sine, cosine, cosine, sine. Cosine, cosine, sine, sine, sine.
Sine, cosine, cosine, sine. Cosine, cosine, sine, sine, sine.
I need y'all to go to your English teacher and ask them what that is in terms of poetry. I feel like it's something.
Golden shovel.
It's not a golden shovel, but sine, cosine, cosine, sine, cosine. So like, let's get the sine alpha plus beta one.
Okay.
Do you want to do another cofunction identity?
Yes. I don't know. No.
Well, let's just use the one we just came up with, right?
Oh yeah.
Sine,
yeah,
cosine,
yeah.
cosine, sine. Let's rewrite sine alpha minus beta. I did that right. Yep. And then let's use the sine formula. Sine, cosine, cosine, sine. Sine first angle. Cosine second angle, which is a negative beta.
But that'll be okay because cosine is even.
Sine, cosine, cosine, sine. I don't change the sign. So I was minus. I'm still a minus. Cosine first angle. Sine second angle. That's going to pop out, right?
Uh-huh.
So the cosine absorbs the negative. Cosine is like Captain America's shield. Did you know that cosine is made of vibranium? It just absorbs all negative signs. That was bad. I'm sorry. And then the negative, I don't have an Avengers analogy for sine though. Does the rhyme still work? Sine, cosine, cosine, sine?
Yes.
Sine, cosine,
we kept the plus.
And the minus, the plus stayed. That is so amazing. Sine, cosine, cosine, sine. Holly, why'd you stop?
Sine, cosine, cosine, sine. Because it wasn't in sync on my end.
Oh, it wasn't. Hopefully it's in sync on my end. And if it's not, I'm sorry, everyone. Okay. Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. That's where we start with sine, and then we get our cosine formula. So we derive cosine first, but the way to remember these is sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. I believe we're not going to write it down at all. So there it is. It has been said 1,000 times. Hopefully it's already in your brain. We got one last one to get.
We could put an audio note on Kami of us saying it, and then They can play it anytime they want.
Oh my
It'd be
gosh,
great.
I'm doing it right
Great
now.
sampling. I don't know if it'll take your voice while you're in a Zoom. But I have to do it in
Sine,
post.
cosine, cosine, sine. Cosine, cosine, sine, sine, sine.
That's amazing. Cool.
Nice. All right, it's in there. We'll get these notes out to you guys. We got one last one to do. We'll use them a few times and then we'll be out of here. This video is getting a little bit long, but I love this lesson so much. I'm so glad, Mrs. Contreras, that you've been having a ball.
So
We went into this one cold, but it is turning out to be great. Okay, got one last one here. Derive the formula for tangent difference and tangent sum.
well, tangent we know is sine over cosine, right?
Tangent of alpha minus beta is equal to sine of alpha minus beta over cosine alpha minus beta. Okay.
So then we could just use what we had before.
Let's see what happens. Sine alpha minus beta is sine cosine. Keep the sine. Cosine sine. Notice we're staying alphabetical. Always. That's why we've set them up in the way we did. Cosine alpha, cosine beta, sine alpha, sine beta. Don't ask me why I put parentheses on that one only. Let's get rid of them. Okay. No, I mean, I guess it's a formula.
Yeah.
What would be nice?
If we had stuff in tangents of alphas and betas, which is not what we have at all.
Yeah. I guess it even asks us to do that. I never actually read the prompt. We want to get tangent in terms of tangent. Okay. This is a completely valid formula, though. Don't get me wrong.
Okay.
You could, to evaluate tangent of pi over 12, you could plug in pi over 4s and pi over 6s, negative pi over 6s all over the place, and you get the correct answer. We need tangents. How can we get tangents?
Can we multiply by some?
Let's some fancy version of one.
Yeah.
I think cosecant. Well, so we need tangents.
Mhm.
So like if we multiply by cosecant of alpha, what are we going to get? We're going to get sine. Wait, we want tangents, right?
We want tangents, so maybe we need to multiply by secants.
Yeah, if we multiply by secant, let me get this right. Secant alpha. Now secant alpha times sine alpha is tangent alpha.
Uh-huh.
Okay.
But then we need to divide by secant alpha also.
I think so. Well, so let me put some parentheses here. If secant alpha times, what's cosine alpha times secant alpha?
Wait,
1, right?
Cosine alpha
times secant alpha.
Oh yeah, because you're distributing. Yeah. I see.
How can I get this sine beta to be a tangent beta?
Multiply by secant beta.
Okay, wait. So if we do this, let's see what happens. I have high hopes.
Okay.
This isn't how I've done it before, but I do have a good feeling. Secant alpha, secant beta times sine alpha, cosine beta. What is that?
Well, the cosine and the secant cancel, so we're just left with tangent alpha.
Okay. Right. The secant beta and the cosine beta cancel, and the sine alpha and the secant alpha become a tan alpha. All right. When we distribute to the second thing, what do we get?
Negative tan beta.
Yeah, the cosine alpha and the secant alpha go away. We get tan beta. Okay. That's the top. Let's see what it does to the bottom.
So we have secant alpha, secant beta times cosine alpha, cosine beta, which is just 1.
That's just completely 1, right? Cosine alpha, secant alpha is 1, and cosine beta and secant beta is 1. That's just completely 1.
And then plus, and we end up with tangent alpha, tangent beta.
Plus tangent alpha, tangent beta. That is elegant.
Cool.
I like that. Multiplying by secants to get the tangents. That was the motivation there. If we multiply by a secant, a sine will become a tangent. There's the formula. Tangent alpha, tangent beta, 1 plus tangent alpha, tangent beta.
That doesn't sound like it has the same kind of ring to it.
No. Let's get tangent alpha plus beta real quick.
Can we do the minus and negative thing?
I like that idea. Let's not even bother with the sine and cosines. Alpha minus negative beta. For people that prefer A's and B's, also that was like an option, but we used alphas and betas. It's nice to see all the letters of the regular alphabet and the Greek alphabet. Tangent alpha minus tangent negative beta all over 1 plus tangent alpha tangent negative beta. And tangent, is that odd or even?
Tangent is odd.
Totally. So the negative pops out.
Yep.
Tangent alpha plus tangent beta all over 1 minus tan alpha tan beta. So there is a song for this one. And I've been teaching this class for going on 4 years. And every year I ask, could someone write me a better song? And no one ever takes up my offer, unfortunately. We will do a formula later that has a song, and I'm still looking for a better one. But anyways, I asked Mr. Stein, who taught me the sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine song. We got to give credit where it's due. And I said, Mr. Stein, do you have a song for the tangent formulas? And he said, I asked my students to come up with the song 20 years ago. And a student came back the next day with the song. And it goes like this. Tangent, tangent, 1, sine, tangent, tangent. And every year I tell everyone this song and they're like, that song's not good. And I say, give me a better song. But here's the thing about this song. Tangent, tangent, 1, sine, tangent, tangent. People remember it. So while it's not that great of a song, it does what it needs to do, and it's remembered by students. I still have students that are sophomores, juniors, seniors that are like, I know the tangent formula because of that terrible song. Tangent, tangent, 1, sine, tangent, tangent. And notice that I say the tangents at the end faster because it's multiplication. And multiplication is faster than addition. Like if you want to add 5 times, that's 5 operations. 5 times 5, that does it in 1 operation. So tangent's faster than addition, so that's why I get faster at the end of the song. Tangent, tangent, 1, sine, tangent, tangent. Notice that I didn't say sine on the first sum, but that's because it didn't change. Tangent, tangent, 1. Then I do say sine, S-I-G-N. If you listen carefully, you can hear the tangent, tangent, 1, sine, tangent, tangent. And if you say it enough, they will remember.
The earworm, right?
It's like, earworm, yeah.
Doesn't necessarily have to be good. Just gotta get stuck in your head.
It's a top 40 hit. Sine, cosine, cosine, sine, cosine, cosine, sine, 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 tangent, tangent, 1, sine, tangent, tangent, sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. That song was in the form ABA, by the way. Okay, let's use them real quick, twice, just to have some examples of them being used, and then we'll get out of here. So, this is where it takes a little bit of brain power, but hopefully I've said it 5 times now. You got this. How can I write pi over 12? In terms of reference angles.
Pi over 4 minus pi over 6.
Is that the only way?
No.
We could do negative pi over 4 plus pi over 6, but that's cosine's even. So that pulling that negative, moving things around, it's not going to change much. Right? There are more than one way to get to these numbers, but no matter what you choose, it's going to output the same value. Let's do pi over 4 and pi over 6. This is equal to
cosine, cosine, sine, sine, sine.
Cosine pi over 4 cosine pi no, not negative. Sorry. Cosine, sine,
Plus.
sine pi over 4. Sorry about the pen. Sine pi over 6. And we know these.
1 over root 2.
1 over root 2. Cosine pi over 6. That's the x coordinate at pi over 6, root 3 over 2.
Root 3 over 2.
Cool. Plus
1 over root 2.
1 over root 2. And
1/2.
1/2. Let me put a multiplication there. Let's simplify a little bit. We're going to get 2 root 2 on the bottom because we have a common denominator. Come on. And then on the top, we're going to have root 3 plus 1.
Mm-hmm.
Sweet. I'm going to go ahead and simplify the denominator. Multiply the top and the bottom by root 2. We're going to get root 6 plus root 2 over 4. Either of these are valid.
Okay.
Sweet. All right, so we can evaluate the exact value of cosine pi over 4 minus, or pi over 12 using reference angles that sum to pi over 12. We're kind of out of luck if we need something like pi over 5. Can't really get that with reference angles. I don't think, at least. There is a way actually to do pi over 5, but we'll say that for another day. Tangent, do you remember the song? Because I just taught you that song. I don't think you've heard that one before.
I hadn't heard that.
You'd heard cosine, sine before, but let's see if you remember it.
Tangent, 1 sine, tangent.
Oh, you do remember? That's awesome. Wait, no, but we need to split it up first. And I haven't split up 5 pi over 12 for us. So I'm going to put that on you. What's that going to be?
So we have pi over 4, right? Because that's 3 pi over 12.
How about split that 5 up into, like, don't worry about the 12 yet. Split that 5 up into things that are factors of 12. I've never thought about how to do this. I kind of just do it, but I think that might be a trick.
Like 2 and 3.
Yeah, like my pen is really struggling here at the end. I'm going to switch out the tip right after this video. But I think that will simplify to something nice.
Yeah. This is pi over 6 and pi over 4.
Sweet. I think we also could have done some sort of subtraction, like pi over 2. We could have done like a 6 pi minus 1. No, that wouldn't work. Maybe 8 pi minus 3 pi. 8 pi over 12 simplifies to something that we know. So there are other options.
I'm writing it because your
Sweet.
pen is struggling.
Thank you.
Tangent, 1 sine, and then what? Tangent.
While you do that, I'm going to show people that there is another possibility using the difference formula.
Whoa.
That's 2 pi over 3, which we know, and pi over 4, which we know.
Mr. Kirk, can you help me simplify this?
Yes, I can. So tangent pi over 6, I'm thinking about slopes. At pi over 6, the slope is root 3 over 3. Even better, though, the slope at tangent pi over 4, at pi over 4, that's a slope of 1.
Okay.
And then we have 1 minus, we already know the two values is root 3 over 3 and 1. So 1 minus root 3 over 3 times 1, but you don't have to write that.
Cool.
Should we simplify it or not?
I think we could, right? Because
there's a little bit of effort, I think, here, right? We need to find a common denominator. Let's just not do it. Let's not make the video any longer than it needs to be.
Okay.
I think everyone has the ability to simplify that. And you know what? Maybe I'll even drop a question right here. Show me that you do.
Cool.
Sine, cosine, sine, sine, sine. Tangent.
Tangent, 1 sine, tangent.
All right. I'm like kind of baffled, Mr. Stein told me that tangent song. I'm like, that is not going to work. And he said the same thing to the kid 20 years ago. And it has lasted the test of time. However, I am still looking for a better song. That would be ideal. All right. That is this video. So go ahead and
We
stop.
did successfully, though. We got always save the crust.
Always save the crust.
That's
I've been
better.
thinking about that every single time I eat pizza. I get to the end of the pizza slice and there's the crust, and I'm like, I can't throw this out. But always save the crust. Does that mean you don't eat it or you do eat it? Let's not get into this philosophical question. All right.
Favorite pie?
Favorite pie? Apple pie.
Wow.
Apple pie for sure. Apple pie. You know, I like a good pumpkin pie. Not a big fan of cherry pie. Apple pie's my favorite though.
Cool.
You got to use different kinds of apples. Different kinds of apples. You can't just. The worst thing you could do is eat a Granny Smith apple pie. Like the green sour apples. You got to like have some Honeycrisp in there and some Granny Smith, and you got to have some Fiji or Fuji. I'm not sure.
Fuji.
You gotta have a variety of apple types. Your favorite pie?
It's a toss up between, but like access to good blueberry pie is difficult. So like I say blueberry, but I don't like it's just I eat it so infrequently that it like, doesn't really count. And then pumpkin pie is pretty dang good. But key lime pie, if you can find a good key lime pie, that's also very, very nice.
I love key lime pie.
More than apple pie?
When I make key lime pie though, I use limes and not key limes.
Wow.
Key limes
They're
are hard
different.
to find.
Yeah, but like
They do.
it's called key lime
I
pie.
know.
It's not called lime pie.
True. All right. Let's get this one closed up. Yeah, here we go.